Hi, I'm Coach Howard. We all know that there is physics in everything around us, everything we do, and of course, there's physics in basketball. We are looking forward to the lecture, part of Michigan's great Saturday morning physics series. Enjoy the lecture and go blue.
Thank you, Coach Howard. I'm physics professor Tim Chupp, and this is Monica Wood, who is the head of the University of Michigan Physics Demo Lab. I want to note that after the lecture, there will be a live question and answer session hosted by Professor Roy Clark, my Saturday morning physics co-host. I came to Michigan in 1991. That was Juwan Howard's freshman year. He was one of 5 fabulous basketball players, and I've been a Michigan basketball fan ever since. So I'm really excited to work with Monica to be telling you about the physics of basketball. Basketball is a wonderful game. It's a game for everyone. People start at a young age and become very skilled. People grow up and get better and better at the game. People can play the game from any point of view, for example, in this wheelchair basketball game. And of course, one of the great basketball fans was President Obama. It's a game for everyone. You can play it alone, and people do. There's one-on-one games, two-on-two games. You can just shoot with another person and play a game that we called horse when I was growing up. And of course, it goes all the way up to the elite championship levels. So let's start by discussing one of the most basic plays, one of the things that everybody in basketball learns early, which is the layup. So here's an example. So there's a lot that goes into that, and of course a lot of physics. So let's think about the elements of this play. There's, of course, dribbling, which is the process of bouncing the ball off the floor. There's usually some spin to that, which is an important aspect of dribbling and the bouncing itself. There's the changing of the speed of the athlete, which is unanticipated by the defender. The reaction time of the defender becomes important. There's jumping, which is, in a sense, defeating gravity. There, of course, is the shot, the touch that the player puts on the shot that makes it more likely than not for this particular play to make it into the basket. And generally, the backboard and often the rim are used for the success and the 2 points that results in. So that's the layup. Here's another layup. That, of course, is the great Michael Jordan, winner of the Presidential Medal of Freedom, among other many awards. So I focus on Michael because he's one of the great basketball players and one of the most beautiful players to watch over a long time. Let's look at that play again. And one of the things that characterizes his play that people always talked about was hang time. What is that? Well, that, of course, is the appearance that Michael is spending an incredibly long amount of time in the air. That's hang time. And really, we're going to now take a look at the physics of that. But before we do, let's consider it a little bit of a quiz. I want you to think about which of these 3 graphs, A, B, or C, actually is the real Michael Jordan in this play. So the answer to this question actually depends on what part of Michael or the player that you watch. This is not Michael Jordan. This is Dr. J doing another amazing thing, spending time in the air and finishing this play. There's another one with real emphasis. It depends on what we watch. Are you watching the ball? Are you watching the player's hips? Or in the case of Michael Jordan, are you watching his tongue? What do you watch? Well, the thing that we can really understand in physics at first is what is happening to Michael's center of mass. So what is the center of mass? Well, here is a picture of Michael Jordan. This is actually from a movie he starred in, a wonderful movie. I highly recommend it, called Space Jam. And in essence, it is the average of the entire mass of the person. And it's somewhere where this red dot is. Okay, so if you draw these two lines, if we were to hang Michael from one shoulder or another, there would be a common line that runs through the center of mass. Now, Monica is going to demonstrate this point that we're trying to make by showing you that there's an object here with two balls on either end that have rather different masses. And you're probably not surprised that in order to hold that in balance as she is now, she has to hang it from a special point that's closer to the heavier one. That special point is the center of mass of this object. So if you could try to imagine a person with all the appendages being approximated by just two balls, this is our physicist model that we start with. Now, there's a light at the center of mass, but there's also a light at the far end here, which may, for example, be a part of an athlete, Michael or Dr. J, in our two examples, that you're actually trying to watch or follow. It could be the ball, it could be the hips, or it could be another part of the athlete. So we're going to turn down the lights, and Monica is going to toss this object. And there are two lights here on the object. And again, one is at the center of mass, and one is somewhere else. And it's going to have a complicated trajectory, but let's see what happens. Great. Now, we don't exactly know what that is going to look like on film, but we do know the physics of that process. And the physics is that the center of mass, once Monica released the object, the complicated object, that the center of mass follows a trajectory that is very well defined and very described in a very straightforward way by physics. And that is a parabola. So let's take a look at how Michael's center of mass would move if the only force once Michael leaves the ground is gravity. So we're neglecting other forces, which really aren't very important, like air resistance in this case. We'll talk more about the importance of air resistance in basketball later. So as time goes on, equal intervals of time, the center of mass, as Michael leaves the ground and makes a vertical leap, but also moving forward, would follow, for example, a path like this. Okay, so that's a well-known trajectory. We call it a parabola, and that is exactly what happens. Now, here's the math. The horizontal velocity, once Michael leaves the ground, is effectively constant. It doesn't change. There's nothing to slow down the horizontal part of his motion. And that is separate from the vertical part of his motion, which is the part of his motion that's affected by gravity. So the horizontal motion is simply the horizontal part of the velocity that he leaves with times time. The vertical motion is first up and then down. Simply throwing a ball up and down is identical, irrespective of the horizontal motion. And that, of course, is governed by gravity. So it turns out that the time in seconds and the distance in meters are related to each other in a very simple way. So the fact that the horizontal and vertical velocity are separate means that if he takes off with a very small horizontal velocity and goes to this height of about a little over a meter that he can jump to, that the up and down part is the same, and so it takes the same length of time, and the trajectory looks like that. If he leaves with a little more horizontal motion, then a little more horizontal velocity, Then the vertical part doesn't change, but the horizontal part does. It goes further horizontally in that time. More horizontal velocity and even more horizontal velocity. So that is one illustration of the separation of vertical and horizontal motion. The vertical motion is always the same, the vertical leap is the same, but the horizontal part of that is what changes here. Back to hang time. Those all take the same time, but notice that every dot is separated by the same amount of time, and there are many more dots in the upper part of the trajectory than there are in the lower part of the trajectory. In fact, in the upper half of the trajectory, there's about 70%, I'm going the wrong way, 70% of the time is spent in the upper half of the trajectory. And that is what the main thing that gives the illusion of hang time. It really is true, actually. It's not an illusion, that the longest amount of the time is spent in the flattest and highest part of the trajectory. Now, a few years ago, I worked with Michigan dive coach Mike Hildy and two of his divers to study a couple of dives and investigate the physics of that. And what's interesting, and the reason I'm inserting this into this particular discussion, is because it's really quite an amazing video, because these divers are doing remarkable things, first of all, from 5 and 10 meters above the water, but second, because it's exactly the same physics. It's exactly the same that the horizontal and vertical velocity are separated. So I want to show you these videos. Here is Allie doing a 3.5 from a 10-meter board. Now, as you think of how remarkable it is that anyone would do that, and with such grace, I want to go back and show it to you again, I think. And she takes off with a vertical and horizontal velocity. The horizontal velocity is not very large, so she doesn't move very far forward, but she accelerates. She's actually hitting the water at about 30 miles per hour, by the way. And this picture shows her trajectory at equal lengths of time, so that's a real thing. This is Colin, and Colin is taking off with a much larger horizontal velocity because he's doing what divers call a hurdle. So there's the vertical velocity and the horizontal velocity. And his dive takes him much further away from the board. But I also want to point out something else about Colin's dive, which is his hang time. Notice that he spends enough time essentially above the board after he takes off vertically. He goes up, and he's spending enough time to do an entire rotation above the board, and then he'll do 2.5 more rotations on the way down. So that is an illustration of hang time in this beautiful sport of diving. So once again, the center of mass follows a simple path. Here are some statistics, data on what Michael Jordan could do. He had one of the larger vertical leaps, just about 1 meter, 40 inches. The time that it takes to go up and down for a 1 meter jump is about 9/10 of a second. The vertical velocity at takeoff is 4.5 meters per second, about 10 miles per hour. So the diver hit the water, Allie hit the water at 3 times that, but of course she went 10 meters and not 1 meter. And his horizontal velocity in a typical amazing play like the one that I showed you a video of is about 5 meters per second, or 11.2 miles per hour. His takeoff angle is just a little under 45 degrees. And the force that he applies to the ground and that the ground applies to throw him into the air to 1 meter height is 4 times the force of gravity when he's standing still, 4 G's, as we say. So I want to move on to dribbling. This is Isaiah Livers, a Michigan player, just recently. And of course, he covers quite a large distance here with one bounce of the ball, a few extra steps, and then a layup, of course. So the aspect of that particular play that I want to focus on is that bounce, the bounce of the ball. So we need to understand, and it's a very complicated thing actually, but we need to understand what makes a basketball bounce. Seems obvious maybe, but let's start to take it apart. So this is a basketball in cutout. Okay, so there's of course the cover of the basketball. That is for street ball, rubber, and for other fancier basketballs, leather. Some more inexpensive basketballs have this second layer called the carcass, which is bonded to the first layer, but in the better basketballs, this is a separate layer. Then there's you can't read it very well, but there's a nylon layer of twine that's wound up here that gives longevity and strength to the ball. And then there's a rubber bladder on the inside, which has the job of holding the air in it. So that's what a basketball looks like if you were to cut through it. Here are some specs on basketballs. They come in many different sizes. It's a game for everyone, and younger players have smaller balls. The men's college game and the professional game uses the largest ball, which is 9.5 inches in diameter. That introduces a challenge, partly because everybody shoots into the same sized rim, but this is a bigger ball. And also the ball, the specification is 22 ounces, which is about 560 to 650 grams. That will be an important number for us. All of the balls that we have up here are in fact of this size 7, a basketball. The other thing, of course, that's pretty obvious about a basketball is it's pretty round, right? Its shape is essentially that of a sphere. And a sphere is a very special shape, of course. And there's some things about a sphere that you may or may not have known, and I'm going to show you a video now that may surprise you, because it's a drop of water falling off a faucet and into air. Let's take a look at this. And below you can see some stills. You know, the teardrop shape that we're quite accustomed to, and you may have thought is in fact the shape of a raindrop, for example, is really only that shape because there are forces, surface tension we call them, that are pulling on the water drop, but also trying to keep a hold of the faucet from which it's falling. And so it goes through a really pretty interesting process in this high-speed series of photographs that's illustrated of separating. And finally, when it separates, except for some recoil, which is not unlike a bounce, the shape that it wants to take is mostly spherical. That shape, as we say in physics, minimizes the energy that is a combination of the energy of the water molecules themselves pulling themselves together, and then what happens at the surface tension here. So this is a very special shape, and it's a shape that water drops take on. There's another important aspect to that shape, which is that it is the maximum volume, the minimum energy and the maximum volume of most shapes that an object could take. Here is a chart of different shapes. Okay, none of those except the last one really look like a basketball, but the important point is that if you look at, for a fixed surface area with some choice of a linear dimension, like an edge or the radius of a sphere, for a fixed surface area, which a basketball basically has by virtue of its structure, okay, by virtue of the 4 layers that we showed you, but mostly in this case the outer layer, the surface area is fixed, and any change in the volume from the spherical shape would reduce the volume. Reducing the volume of the air in the basketball when we press on the basketball, for example, will reduce the volume of the air, and the air will respond. And that is a major part, but not all, of what goes into the bounce of a basketball. So let's take a look at another video. Of a basketball bouncing, one more time, out on the driveway. Now I'm going to freeze that video right as the basketball hit the ground. And you can definitely see that the shape is, well, it's no longer a sphere. And in fact, the basketball, therefore, has a somewhat smaller volume, and the air inside the basketball is going to help it respond or bounce. So the air is like a spring, and we're going to demonstrate that to you. So let's take a look. Are we ready? Good. All right, so what we have here is a, well, it's a piston. All right, so it's a device where here there is the piston itself. It's connected to this rod, and it's sealed pretty well against this glass cylinder here. And it's sealed well enough that if I push down on this, you can see that the pressure gauge is indicating increasing pressure. So we're keeping track of a couple of things here. We're keeping track of the volume of the cylinder, which is decreasing just as the volume of the basketball decreases when it deforms. And we're keeping track of the pressure. And in order to do this in a really calibrated way, because this is not calibrated, I'm pushing on it, we are going to use masses, different masses here. So this is an interesting device. You can see that it gets a little sticky from time to time. But nevertheless, let's just keep an eye on the dial. And the units on the dial actually are hundreds of kilopascals, HKPA. That's kind of a cool unit. If you want to know what that means, 100 kilopascals is the difference in the pressure between the atmosphere in this room, in essence, and if the room were evacuated. So the difference between normal air pressure and a vacuum. There's some offset here, which we can compensate for. And if I put a 1 kilogram mass on there, 2.2 pounds of force, or approximately 10 newtons in those units, it increases the pressure a little bit. And it recovers. I have a 2 kilogram mass. More. I hope you're all writing this down at home. A 5 kilogram mass. Definitely more. And it's even possible to do 2, 4. 4 plus 5 is 9. And I don't dare put another one on. So I can go up to 9. In fact, I did write this down the other day when I did it. So I'd like to show you what the results are. Now, I'm going to show you a graph that is showing the pressure versus, which is on the vertical axis here in these units, not versus the volume, but versus the inverse, 1 over the volume. And this means that going to the right on this graph is a decreasing volume, and going up on this graph is increasing pressure. And you can see it's pretty close to a straight line. It's not, those are real data, those dots that I took. But the point is that the air acts like a spring. If I push on the air pushes back. And this is characterized by a pretty simple equation. The amount of extra pressure that's provided, pressure is the force per unit area, is related to the fractional change in volume, the change in volume divided by the volume. And there's a constant that characterizes the material. In this case of this example, air, but in the case of the basketball, it's actually this complicated combination of air and the rubber that the basketball is made of. So the coefficient of restitution is a way to characterize an aspect of the recoil, how much something pushes back, but also how much energy is lost in the process here. So the main reason, are you doing that one? Yes, the main reason that we're showing you this is that it's even more complicated. Monica is going to drop several different all balls of several different materials from this object, which is an anvil, which won't recoil and is a very hard surface. So go ahead and pick one, a ping pong ball.
Ping pong ball. Tennis ball. Ball bearing.
Steel. So that pushes back pretty hard. And the last one is a very interesting material because it's rubber, the same material that makes the shell of the basketball. And look how close to where she dropped it comes back to. So on our graph here, we show how these various different materials, including a basketball, a typical basketball. This is an experiment we should do as well, don't you think? Recoil. But a basketball, again, has this combination of rubber, which is this one here, and the air pushing back. So we call this the coefficient of restitution. Now, back to dribbling. Monica is going to dribble a bit, but in order to dribble, you actually do a lot of work. You push the ball pretty hard down from a height, which is about 0.5 meter in this case, and the ball recoils. And of course, a basketball player is going to be doing that, and every time the ball comes up, we'll push it back down with the hand, maybe put some spin on it to help make a move, etc. So what Monica's going to do is dribble the ball for a little bit, but then after making a move perhaps, she's going to not catch the ball when it comes back up, not stop the ball. And we just want to see how high it goes. All right? So we might do this more than once, but go ahead. Now you did appear to push it a little harder at the very end, maybe a little more naturally this time. Okay, so that height was above Monica's head. It was probably about the height of my head, so it's somewhere around here. And when we did this experiment before, it was a little bit higher and lower. We have a 2-meter stick here, and that height is, well, it's about 185 centimeters, 1.85 meters. Right. Now, to make my life simple, I'm going to go back to an earlier one, or when Monica did this, and it was just about 2 meters. Now, the basketball started from a height of about, well, we'll say half a meter because, you know, a basketball player is usually down low. And in order to go from the floor to 2 meters, the amount of gravitational energy is m times g times h. The mass of the ball, g characterizes gravity, and h is the height. So to go from the floor to the height of 2 meters, well, we have to know the mass of the ball. So we just happen to have a scale here. And the scale is zeroed, so we'll put the basketball on the scale. And it's 587. The scale is in grams. So that's the mass of the ball. We like to use kilograms. Got that? Kilograms. And the height is 2 meters, right? So in order to make the basketball get to a height of 2 meters, if she started at the floor, it would be the mass of the ball times g times 2 meters. But she did not start at the floor. She started at some height a little bit above the floor. And when the basketball fell, there was some energy gained. When the basketball came up to that height again, that energy was lost again. So we have to be careful and make sure that we include that. So that's the amount of work per bounce. If all of the energy were recovered. But of course it's not. Only about 60%. Which means that Monica actually had to work harder than that. And the question is, where's that going? So I'll bounce it. Well, you're the bouncer. Looks like a bouncer. Okay. So one bounce is enough to let you know that you heard it, right? A second bounce, just in case. There's no question. This is the sound of basketball. It could be on a street, it could be on a wooden floor, or it could be on our floor here. No matter what, it makes a sound, and there's no question that it's basketball. It's kind of a special sound. But that sound takes some energy to make. So that's one. But there's actually probably a more important place where the sound goes, and that is into heat. So we've devised a little experiment. It's a little bit of a risk, but we decided to give it a try. What we have here to show you is a special camera. This is an infrared camera. You can see that it is giving a kind of heat map of what it's looking at, and Monica could put herself in front of it or her hand in front of it. Probably yourself is better, right? So there's surface temperature of sort of on the order of just over 30 degrees usually. And the crosshairs are showing where a temperature is being measured, and in the upper right is in fact the temperature. And it's reading 22.5 or so. And that is the blue stripe on the ball, actually, that we're measuring right now. Now, we think that some of the energy that is being lost in the bounce of the ball is going into this form of energy we call heat, which would lead to a rise in temperature of the ball. So we're going to check it out and see how it goes. So we start at 22.5. Now, Monica is going to bounce the ball a large number of times. I think we agreed on 50. So go to it. 2, 3, 4, 5, 48, 50. And let's see. Well, now it's cooling off a little as we wait, but 22.9. So it seemed to have risen with 50 bounces about half a degree, from 22.5 to 22.9. Let's call that half a degree. That means 100 bounces would be a degree, or 1/100th of a degree per bounce, which actually is what we saw before, so we wrote it down. Maybe I wrote 0.01 to 0.02 degrees per bounce. Okay, now we know the amount of energy that's lost. Let's just say all of it goes into heat. It's not much into sound, the 9.5 joules. And if you then do one more physics calculation, which relates the amount of heat transferred to or from an object of mass m, 587 gram basketball, and its temperature changes in amount delta T, in this case for each bounce 1/100th of a degree, then there is a quantity that characterizes the basketball, which I did not see specified in any of the catalogs or any of the NBA rules about the basketball, which is the specific heat of the basketball, 1.6 joules per millikelvin. All right. One more thing, this will take just a minute to recover, is we actually have several basketballs, as you can see. And because this is Michigan, some of our basketballs are Michigan basketballs, and we wondered what would happen to a basketball if it was cold. Okay? You left it out in the snow. And so we figured, this being Michigan, that the right basketballs to use for that demonstration is the Michigan basketball. So Monica here has these two basketballs. The one in her left hand, this is an experiment we haven't done before, so it'll be interesting to see what happens. What do you think is going to happen? The basketball in her left hand has been in the freezer, so that's a temperature near 0 degrees Fahrenheit. And the one in her right hand has been sitting in this room. In fact, she just bounced it 50 times. So let's see if you're right.
3,
What do you predict?
2, 1.
Any surprise? What happens when a basketball gets cold? You could do it one more time.
3, 2, 1.
What happens when a basketball gets cold? Well, something changes to the air inside. All right. As the temperature decreases, the pressure decreases. For one thing, the nature of the rubber changes, but for a large combination of reasons, there's no question that a cold basketball has a much lower, it's cold, it's very cold, much lower coefficient of restitution. So let's move on to shooting. Of course, the objective in a game of basketball is to shoot, in the case of the 9.5-inch ball, through an 18-inch hoop that's mounted 10 feet above the ground. In fact, that 10 feet is pretty much seems to be used at all levels of competition. I looked at a lot of videos. Now, that looks pretty easy the way I drew it, right? There's 18 inches, 9.5-inch ball. That's 8.5 inches divided by 2. There's 4.25 inches on each side of the ball all the way around to get it through the hoop. So that's easy, but who drops the ball straight through the hoop? How often does that happen in a basketball game? What happens, of course, is that a player shoots the ball. And the ball is shot. Okay, we saw this before. This is the same physics to begin with, if we consider that only gravity is acting on the ball. Actually not a very good approximation for shooting a basketball, but let's start there. That's because we have to neglect aerodynamics, or the effects of air. Playing basketball on the moon, all right? Of course, the gravity on the moon is different, so the amount of work and all of that would change. It would be a different game on the moon, for sure. But what is true is that the basketball in a shot is launched with both a horizontal and vertical velocity in general and follows a trajectory. And that trajectory with no aerodynamic forces is shown here. You have to keep track of many things. You have to keep track of how high above the ground the shot left from. You have to keep track of the angle with which the shot left. The maximum height is not particularly important to keep track of, but it is part of understanding what's going on. And then the ball has to hopefully fall through the hoop, but it's no longer falling through the hoop at a being dropped straight down. It's coming through at an angle. And that produces a challenge in its own right. Now, that 4.5 inches, if you drop the ball straight through, is affected by the angle that it goes through the hoop at. But we're going to give it a kind of a fancy term, the margin of error. All right? So what I want to show you with a demonstration here is what happens when the ball comes at an angle. So we have a ball here, okay, and this ball and a hoop, and this is projected on to the board so that you can see what happens. So, of course, if you were to drop the ball straight through the hoop, it would essentially be like that. And you can see the margin of error is the rim between the hoop and the annulus between the hoop and the ball and their shadow. Okay. Now, if the ball comes down at an angle, okay, let's say 45 degrees, then you can see that the margin of error has been significantly reduced, at least in the vertical direction in our example here. And 45 degrees is not unusual. So it's a lot harder to make a shot in terms of how big the rim seems to be when you're not shooting from straight above the basket, which is not part of the game. So that effect, plus the fact that we can calculate what initial velocity, again neglecting air, what initial velocity is needed to launch the ball, which is simply depends on how far the player is from the basket, how high the player is launching the ball above the floor, and of course how high the basket is above the floor, which is 10 feet. So there's a formula here. What matters is that without air resistance, you can calculate that in a straightforward way. To include air resistance is also straightforward, but more detailed and doesn't assist our understanding. So let's take a look at this margin of error in a different way. Here we have on the left the ball dropping straight down. And the margin of error is 8.5 inches. That's the difference between 18 inches and 9.5 inches. If the ball's coming in at 60 degrees, then the margin of error is reduced to 7 inches. Okay? So the rim, as the ball sees it, in this direction is less, it's 7 inches. And the velocity with which it needs to be launched from any distance is 9 meters per second, from a typical distance of 14 feet, actually. In order to get a ball to come straight down from 14 feet away, you actually, in principle, have to launch it with an infinite velocity. That's hard to do. In fact, 9 meters per second is harder than 6 meters per second. So if the ball comes in at 45 degrees, it actually requires less oomph to push the ball to give it an initial velocity. So you need a smaller initial velocity. It doesn't have to go as high. But the margin of error is significantly reduced. So shooting becomes a balance of these two factors. Okay, how hard you throw the ball, and the harder that you throw the ball, or I guess we call it shooting the ball, the harder the push on the ball, And therefore, the greater the initial velocity, the harder it is to control. Okay? You just have to push harder, and it's harder to control. So that makes it more difficult, but so less initial velocity, however, has a smaller margin of error, which also makes it more difficult. So, this is actually a hard thing to do, learning to shoot a basketball. And there are people who are incredibly good at it. And how do they do that? Well, they haven't actually probably worked through any of the physics that we've been discussing here today. I think what they're doing is practicing. So I want to take a look at a few shots. This is an iconic, possibly the most famous shot, at least in recent history, by a Michigan player, and that player is Jordan Poole. So just like the layup, there's a lot going on. The player had to receive the ball. Jordan had to set himself. He had to release the ball. He had, to get to the point of releasing the ball, he had on the order of just over 2 seconds. But once the ball was in the air, let's look at it again. One of the things I can't explain the physics of in this is why he splays his legs. No problem. There's probably physics in that. Here's the trajectory of the ball with equal times shown here in that slow motion shot. So the red pieces of the trajectory are while he's holding the ball, and the rest of it is while the ball is in the air. And I was watching the game clock as the video was going, and it was right about at the peak of this that the time ran out. So there's no question, though of course in the replays they discussed this extensively, whether he got the shot off in time is the way they put it. But he did, and Michigan won this game and moved on in this tournament a few years ago. Here is a current teammate of Jordan Poole, who's considered one of the best three-point shooters or shooters that there is in the NBA. This is Steph Curry. And there's a lot about that shot that we can take a look and analyze. So here are a couple of stills from the shot. Of course, this is where it all starts. It hasn't left his hand. It doesn't have the initial velocity. It's not under the influence of just gravity and aerodynamic forces, of course, until it leaves his hand. And you should also notice that he's clearly pushing the ball in this direction. Okay, so that gives the initial velocity and direction to the ball. But also, as soon as the ball reaches, the ball leaves his hand, he pulls his wrist down and gives the ball backspin. Let's take a look at that backspin. There's no question that ball is rotating backwards. And that, I understand, the basketball players call the soft touch. Now, what is the effect of that? Okay. So remember that we have the margin of error that characterizes how hard a shot is. And it's better to drop the ball from straight above in the air. Here's another soft touch that I like. What causes the soft touch is backspin. So this is where we're going to start with this discussion with the basketball moving through the air under the influence of gravity. Okay, so it's moving through the air. So gravity is clearly a force that's acting on the ball. And at the instant in time that I've drawn this picture, it has a velocity in that direction, pretty much the direction of the ball when it left Steph Curry's hands in the pictures that we just saw. Now, the ball is moving through the air, and one of the features of the air, the aerodynamic forces on the ball, is simply that the air is pushing back. The ball is trying to push the air out of the way, and it's basically a wind. We call it drag. There's a force or air resistance. So let's call it drag, and that is opposite the velocity. But that's not all. The ball is also spinning. It has backspin. And as a consequence of its spin, let's just do some investigations. What happens? So Monica is going, we're going to do this one first. We're going to investigate what happens when the ball spins. So we have here a basketball, and we sort of made our own wind tunnel. And the way a wind tunnel works is that you have a stationary object that would normally be moving through the air, and you make the air move with respect to the stationary object. And then you try to take pictures or videos that illustrate that. Now, we're going to use smoke. This is incense. We forgot to cue the right music for this, but that's okay. So there's the smoke. And it's giving us some idea of complicated air movement in the room. Now let me spin the basketball. And move the smoke closer to the basketball. So keep an eye on this. Right near the basketball, the smoke seems to be picked up and pulled around in the direction that the basketball is moving. And that's because there is a layer of air that's essentially attached to the basketball. We call it a boundary layer. And many spinning balls have this layer. All spinning balls actually have this layer. But it's complicated and depends on the particular structure of the ball, the little dimples in the ball, golf balls, baseballs with threads on them, etc. So there is this layer of air that's moving around with the basketball. So we'll draw that into our picture of the spinning basketball, this boundary layer. And that boundary layer is moving, thanks for putting that out, the boundary layer is moving in the direction of the spin of the ball. That means that at the top of the ball, the combination of the wind, as the ball moves through the air, and the boundary layer, the air is moving faster on this side of the ball. And on this side of the ball, the boundary layer is opposing the wind, and so it's moving slower. Now, there are a lot of important aerodynamic effects that result from the velocity of the flow of air. Monica's going to demonstrate one here with a beach ball. And again, we have to turn around our reference frame. Instead of a ball moving through the air, we have a stationary ball and make the air move. Okay? So you want to try spinning it? Okay, let's see what happens once you spin it. Okay, as it slows down, it's moving that way. So let me try to describe the observations, okay? First of all, there's no question that the ball is suspended as the air rushes around it on both sides. And when the ball was not spinning, it was a simpler situation, there was air pushing straight up on the ball, but also air going around the ball faster. And the faster air has this feature of being a lower pressure. This is very familiar in a lot of ways. We call it the Venturi effect. So back to the basketball with the, and when Monica spun the ball, there was a difference in where the ball wanted to be positioned with respect to that. So the balance of forces was different with the spinning ball and with the non-spinning ball. So back to our picture here. The wind speed at the top is larger, at the bottom it's smaller, and that results in a greater pressure at the bottom than at the top, which pushes the ball in the direction perpendicular to its velocity, which is mostly upward, actually. So that gives it lift. Now, this effect, aerodynamic effect, is called the Venturi effect, and it is one of the main ways in which an airfoil works. So sailing a boat or a flying airplane works because the velocity of air over the top of the wing is greater than over the bottom of the wing. That produces more pressure at the bottom than the top, leading to lift. Okay, so that's why airplanes work. So just to review here, spin gives lift to the ball, and that extra lift affects the motion of the ball. It softens the ball so that, well, let's just try to see what happens when we do this demonstration. So what Monica's now going to do, in the dark, so we have a basketball here. There's a light on the basketball that's at the center of mass, but also the center of the potential rotation axis. Monica is first going to, she's very good at basketball, she's going to do a basketball shot with no spin on the ball. All right? And let's take a look at the trajectory, which will be traced by that light, that little light. So that was a non-spinning basketball. And now she's going to do a soft touch shot with backspin. Now, if you didn't track that, we did. So I'd like to show you what those two shots looked like. So first of all, this is the light. You can see Monica throwing the ball there. And as she got it started with no spin, it follows a trajectory that looks very much like what you'd expect, at least to the eye, the parabolic trajectory of an object where aerodynamic forces are not very important, mostly and only gravity. But look what happens to the shot that she put the spin on, the soft touch, the backspin. Notice how the ball doesn't look like it's following a parabolic trajectory at all, number one. And number two, how much more vertical it is at the end of the trajectory than at the beginning of the trajectory, because of the combination of lift and the ball slowing down. So in essence, this is getting much closer to that ideal of being able to drop the ball through the hoop, the soft touch, ball with backspin. So this effect is called the Magnus effect, and not surprisingly, it affects spinning balls of all sorts, not just basketballs. So, and balls, of course, are used in many, many different sports. So I just have a little gallery here that I'd like to show you of other sports. I brought diving in, now I'm bringing in soccer. This is Lewandowski. Okay, so that's not backspin, that's sort of side spin, and look at the bend on that ball, the curved ball. goalkeeper must know it's coming, but still cannot adjust to that. So it's really a remarkable thing. Okay, so that's soccer or football. Baseball. This is painful to watch, but pretty amazing. I think this pitch is called a slider. We can analyze this pitch, but I really just want you to see that as I move forward in slow motion, that the ball is spinning around a sort of strange axis, which has established the spin by the way it leaves his hand, and that strange axis also by how this seemingly contorted thing. Hitting a ball a long way with a bat. Okay, there's several things going on in this picture, the bat's bending and all of that thing, but also this ball is getting backspin as well, an extra lift, right? And that helps it defeat some of the drag and aerodynamic forces, and is one of the features of the home run swing in baseball. Tennis, of course, round balls. So here is Federer. I think this is hitting a ball with topspin. Spinning balls also impact another aspect of shooting in basketball, which is using the backboard. So I want to discuss that for a few moments here. So remember that most shots are made with backspin, some kind of spin, usually backspin. And let's consider what happens as a basketball with backspin approaches the hoop here, which has, of course, a lower margin of error because of the angle that it's coming in here. So it's a spinning ball. Okay, we're neglecting aerodynamic forces, but this ball is going to hit the backboard, right? And when it does, spinning in this direction, the ball is going to exert an upward force, right? There's friction between the ball and the backboard when it hits the backboard, and the ball is going to sort of scuff up a little bit, push up on the backboard. And we know from Newton's third law that if the ball pushes up on the backboard is pushing down on the ball. So if that weren't the case, without Newton's third law, it would simply make a mere reflection bounce like that. But this trajectory that I've shown here is neglecting that force of the backboard on the ball. That extra force leads to this trajectory, and the ball goes through the hoop. Again, with a smaller margin of error because it's a more vertical path. So that's using the backboard. This is another interesting shot. You see this more often than you might imagine, that the ball kind of scuffs on the front of the rim. Okay, it's a little bit low, the shot, but somehow goes in. Oftentimes, balls seem to linger for a very long time near the rim and fall in. And this is also can be understood in terms of the spin on the ball, that there's a ball that would normally bounce off the rim in an odd way. This extra little bit of force helps it roll over and fall into the rim. Another example. So I want to finish up here with a very important aspect of all sports that are played with an opponent in particular, because it's sometimes hard to understand how it is that an athlete cannot defend a particular move, for example, by a basketball player. How can a player accelerate enough to get through a small gap and to the basket to make a layup, for example? And I'm summarizing that rather briefly here by telling you that, of course, this is because even the best athletes, the most elite athletes, have a limited time that it takes them to react to an unexpected move by an opposing player. Monica is not an opposing player, but we do an exercise as often as we can demonstrating the limited reaction time. And it's pretty straightforward. We simply do something, one person does something that the other person doesn't expect, and we figure out how long it takes them to react. So in this case, it's very simple. I'm going to, the reaction is Monica catching the yardstick when I drop it, but she doesn't know when I'm going to drop it, and I'm not going to give her any cues. And then the distance that it falls before she closes her fingers and catches it or stops it from falling, the distance becomes directly a measurement of that time. And anyway, she doesn't know, but I'm going to at least not totally surprise you. Okay. It's always embarrassing, but that was about 22 centimeters. That's really good, actually. That's very good. All right. So I've done this experiment thousands of times with classrooms filled with students, this room filled with Saturday morning physics patrons, and in fact, whenever I can. And the answer is remarkably tightly clustered around 170 to 200 milliseconds, 0.17 to 0.2 milliseconds, seconds, excuse me. And we can also understand that there are several aspects to that, right? Monica was not expecting me to, she was expecting me to drop it, but she didn't know when I was going to drop it. So there was an unexpected aspect to that. So she had to notice that it was falling. Her eyes had to see it. Her brain had to process it. And then her brain had to tell her fingers to close. They were ready to do that, but nevertheless, it takes time for the nerve impulse to travel from the brain to the fingers. And we've taken that apart many times. The time it takes to notice something is on the order of 1/30 of a second. You may know that old-fashioned television sets, earlier computer monitors before gaming became the main reason that people got computer monitors and so on, refreshed at 30 times to 60 times a second. That was sufficient for us to look at something and perceive it as motion as opposed to individual frames. So 1/30 of a second is about 30 milliseconds. The nerve conduction velocity on skeletal nerves is about 100 meters per second. It's about a meter, so that's 100th of a second or 10 milliseconds. You add those two together, and you don't get anywhere close to 200 milliseconds. And the reason is that the real limiting thing is how fast any person's muscles can do what you're asking them to do. There's a limited strength, whether it's responding to a move in basketball or catching a falling ruler. And we've done this investigation for the falling ruler as well and found out that it's 120 to 140 milliseconds. So the very best athletes, you may know, are very strong in the sports where this is what matters and have particular muscles. But in the end, that is the limiting thing. That's what limits reaction. So let me summarize. We've talked about many, but of course not all, aspects of basketball, the physics of basketball, the amount of force at takeoff, the amount of time in the air, hang time, the soft touch, and swishes. And I think there's no better way at this time of year to present it than with a bracket. Thank you.
Well, awesome. Hi, everyone. I'm Roy Clark, professor of physics and Saturday morning physics co-host. I want to start this question and answer session with a big shout out to the team responsible for today's fantastic presentation on the physics of basketball. First, Monica Wood, the manager of our lecture demonstration lab, for putting together the great demos that I hope you all enjoyed during the lecture. And my co-host, Professor Tim Chup, who's doing double duty today as both host and speaker, for helping us to better appreciate the science behind this magical sport. How magical? Well, if you watched the game a couple of days ago, the Big Ten Championship, that's how magical. So congratulations and go blue to the U of M men's basketball team and Coach Howard. So there it is. So yeah, we've got a whole bunch of really great questions from our viewers. So let's get to it. Our first question is from a student, Cade, who's only 6.5 years old, and he's really into both physics and basketball, obviously. And he wants to know, what is the best strategy in basketball to win the game? Ultimately, I guess that's what is the most important. So, either of you.
Wow. Well, thanks a lot for that question, Cade. That's a great question, and I'd like to say that the answer should be that the more of the physics of the game that you understand, the more likely your team will be to win. But actually, I think there are really two aspects. For individuals, it's what we all recognize, which is practicing. And maybe knowing that the reason that you put backspin on the ball is to give it this extra lift and soften it and make it come down more vertically through the basket will help you tolerate the practicing when your coach tells you to do it again, do it this way, make this small change. But the other aspect of this game, I believe, and so, I'm not speaking with a lot of authority, but it seems to me that what really separates the best teams, all who can do the scoring plays, what separates the best teams right now seems to be defense. So I would focus on that aspect of the game, which is also a lot of practice and learning strategy and being able to compensate for your limited reaction time. And good luck, Cade.
Yeah, good luck, Cade. So this is a really interesting question, and it's about footwear. This has clearly been a little bit of a contentious issue throughout the recent history, especially with marketing and how much science versus how much hype, and in particular, how significant are the elastic, springy properties of various various basketball shoes in regard to hang time and jumping height? And is there a need to regulate this? I know that the NBA has been pretty serious about its uniform code. So could you address that, Tim?
Well, I'm going to address the impact on the sport explicitly. There are a lot of sports, all sports probably, where evolving technology becomes part of the sport. And basketball is one of them. So that's, that's up to the sport and the way people play it and the way people take advantage of that. But in terms of the simple physics, to reach a height H, neglecting aerodynamics requires a certain amount of energy, depending on the mass of the player and gravity. It's as simple as that. And unless the shoes are somehow self-powered, rocket shoes or some sorts of energy in the shoes themselves, they're not going to provide extra energy or extra lift. So that's the simple physics of it. Exactly how the technology of a shoe seems to benefit jumping, I actually I don't know what that is, but I'm sure that there are aspects of shaping a shoe that help align the leg and the foot and so on to make it more efficient and less energy loss, which would allow an athlete in principle to go a little bit higher.
All right. Now here's another Great question. And it's to do with backspin, which you pointed out in your lecture is really important. So the question is, how consistent are aspects like the amount of backspin among great shooters for individual shooters and between different shooters? Can it be that too much backspin would come with a penalty, such as the amount of energy it takes to put the spin on the ball, perhaps resulting in less consistency at higher backspin? So that's a little bit of a technical question, but it's very important.
Yes. It's a complicated question, and the answer will be imperfect or effective. So I have not analyzed a lot of shots to measure backspin rates. That would be really interesting. A hobby, I would say. But I think my observation of players is that players can score from all sorts of different positions. So Jordan Poole shot as an example we showed, but players are shooting from they have favorite spots and they have cues that help them understand where they are with respect to the basket. But they can score from everywhere, and every different position, every different amount of motion that their body must make because of the opposing, the defending player who's going to be there. Every one of those is going to require some adjustment to the trajectory that's given to the ball. And it's just amazing that the players can do that when you realize, just these few variables, but they are variables, and quantitatively, they're going to be different. That people learn to make these adjustments. Practice, practice, practice. But you could certainly put too much backspin on a ball. The sort of backboard shot that I illustrated, where the spin helped it go in, that made it come more straight down, and so we now understand how important that is in scoring. But if there's too much backspin, it could hit the back of the rim and things like that. So yeah.
Yes. So here's a related. I think this is related. Maybe it is. Maybe it's not. But from a physics perspective, would a return to the underhand free throw be advantageous?
Maybe Monica wants to take that one, because she'll tell you how she managed to make the two shots that we showed you showed you the trajectories of.
Absolutely. So the shot that I didn't put a spin on, the path that it takes is fairly predictable. But when you saw the comparison of the shot that I put the spin on, you'll see that it fell at a much higher angle to the vertical. And so it was able to fall more straight down into the actual rim, allowing for a larger margin of error, which would make the shot more likely to actually happen. So the backspin is a pretty important aspect of shooting, especially to increase that chance to go in and actually make the shot.
So Monica, I know in some of your, you did this many times, and in some of the shots with no spin, you actually did do the granny shot, so to speak.
Yes.
Right? So the question, I think there was a question, was this the question about whether this underhanded or granny shot type thing would have an advantage? And we know, I guess, is that, yeah.
I think it would if you were able to, do it for your the penalty shots and things like that, where you're at the same spot each time. Then you would be able to really hone in exactly how to do the shot. You know exactly where it's going to go, so it definitely has an advantage. It's just a little silly.
So I think this is true, that it would be hard to put backspin on a granny shot. Topspin would be more
Kinda-
likely. So yeah, right. So topspin is harder.
Yeah.
And sorry, topspin makes the shot harder instead of softer.
Yes.
So the tennis players put topspin in order to hit the ball harder, and there's a downward aerodynamic force due to the topspin.
Yeah, so there's a really interesting question here about something that has been a very important question in some other sports, and in particular football, and it's to do with overinflating or underinflating the ball and its effect on dribbling and shooting.
Mm.
So-
Right. So another controversy. Well, so a basketball is inflated to around a little over half of the pressure of the atmosphere above the atmosphere. So it has a higher pressure. If you recall the discussion, there's the quantity that characterizes the material, and actually it's a little more subtle. For air, it depends how the pressure is being applied, what the situation is. We called the bulk motions. It's just a measure of how much it pushes back when you push on it, how much the fractional volume changes when you push on it. That is proportional to pressure. So if a ball has less pressure, it will push back less for a given deformation, and if it has more pressure, it'll push back more. So I've been told that the referees who in basketball games who need to, there's a specification, this 8 pounds per square inch for the amount of inflation, but they don't actually use a gauge on every ball. They just bounce them. They just drop them and see how far they come back. So in a sense, they're measuring by the response of the ball to being dropped. That.
Which is really the most important thing, yeah.
Yeah, the other point. So I think a player doesn't really want to have a ball with a different feel, a very different feel. They want to have the same thing every time. Unless that's not true in baseball. A pitcher would like to have a ball that's different on every pitch, so that it would be less, more surprising to the batter. And they make an effort in professional baseball, like every 3 or 4 pitches, there's a new ball, so that they're almost all the same. So I'd imagine that the players would prefer to have the ball be consistent and the same, which includes the inflation pressure.
There's a related question, and that is again to do with the inflation of the ball and what you put inside the ball. When you go to get your car tires checked, they sometimes will recommend putting in a different gas or a different mixture inside your tires. And the interesting question here is, what's the best gas to use? Oxygen, nitrogen, helium? If you use a molecular gas or a atomic gas or a so-called gas that's closer to being ideal, what are there any regulations about that, and what effect does that have on dribbling and shooting? Has that been explored? I don't know. I'm not aware of that.
So I can tell you some things about different gases. So helium, of course, everybody knows that if you put helium in a balloon, the balloon weighs less than the amount of air that takes up the same volume. So there's an upward force, buoyancy. Well, there's always a buoyant force. It's actually, there is a buoyant force on a basketball, by the way, as well, but it's very small compared to the other forces. So anyway, helium would definitely change the weight of the basketball for one thing. But there's another aspect that's a difference between nitrogen. Air is mostly nitrogen and oxygen. Those are both gases that have two atoms in every molecule, so diatomic gases. And they actually have a different response for a given amount of that gas in the basketball than helium to the deformation. So this actually, it's a factor of about 2.5 different, I think, 5/3, whatever 5/3 is, so a little less than 2. So that, is a practical difference. Again, I haven't analyzed it. I have lots of things to go off and do now with great questions. And then, other gases would be pretty expensive. Now, the other thing about nitrogen compared to oxygen is that, the air is being held in by a rubber bladder, by an inner tube, or other aspects of a tire. So I believe that oxygen has an effect on the aging of the rubber, and it changing its properties. Can't hear you.
Roy, you're muted.
Yeah, so lots of aspects which come into the details of the physics, which haven't really been explored. And I guess it's a very empirical science as well over the years. That brings up one question that I had and that was about the construction of basketball courts, which are generally I guess hard maple is widely used, but there are other types of wood and plastics as well that are in use in different basketball courts around the world. So these have different elastic properties for jumping, especially. So, do you have any comments about the kind of interaction between the feet and the court?
The feet or the ball on the court.
And the ball on the court, yeah.
Yeah. So basketball can be played on a lot of surfaces, but they basically need to let the basketball bounce. I'm sure that the game on sort of asphalt or other things are concrete, cement courts, etc., street ball. It's just really different, and you have to make adjustments to it. I think the sound of the ball bouncing is different, so that indicates the differences here. I have not reviewed what kind of specs there are on courts. Do the courts have to have in some way, what are the specifications for a court that you can play an NBA game on or the college game on, etc. But that would also be interesting to consider.
Good. Well, we had a number of really interesting questions, and I think we got to most of them. I want to finish up with a kind of personal touch for our speakers today, to ask them how they got into the physics of sport, and from a personal perspective, how did you get interested in that area? So, Monica, do you want to go first?
Sure. When I was a kid, my dad played a lot of baseball, so I've always been into sports. But I always liked basketball more, playing horse and one-on-one with my dad and later my brother. But then in high school, I had to choose band over sports, so I got pulled away. But after getting into physics and really landing the job here at U of M, I've been able to explore a lot of areas that I didn't get to before, and sports, I get to have the love of it again. So it's always fun to return.
Yeah, perfect. Tim?
Oh yeah, well, so I've been moderately athletic, maybe overly athletic sometimes, my entire life, and I've also been thinking like a physicist for most of my life. So, in a sense, I'm putting together, but for me, the physics of sports helps a bit in my enjoyment of the game, but I see it more as a way to sort of teach physics, and in particular, physics that we encounter every day. So it's a privilege to be able to give lectures to groups of all ages, from preschool to Saturday morning physics audiences that are not, my day job, my normal job of teaching physics. And at some point, I had a high school group come in that gave me I said, well, what might they be interested in? And I just thought I'd talk a few things about sports, and it's been a growth industry ever since. This is the latest.
Yeah, definitely. All right.
All right. Oh, by the
So,
way, go blue.
Yeah, absolutely. So I think that wraps it up for today's program. Sorry about the the hiccups with the audio at the beginning, but I think we got over that. I want to thank Tim and Monica for a wonderful talk on the physics of basketball. And a special thank you to all of our loyal supporters in Saturday Morning Physics. Our appreciation also goes out to Carl Cole and his video production staff at Michigan Media, and to our communications director, Carol Raybert, for keeping us all on track. 2 weeks from now, we're going to have a really interesting lecture on the science of COVID-19 vaccines. That'll be on the 20th of March, and presented as a special Walker Family Memorial Lecture. And we look forward to seeing you all then. And again, go blue.